In the first video, I just want to give a little introduction to these things called sets, so we can use them to talk about some other concepts. We'll get into the sets in much more detail in a little while, but before that I just want a little introduction so we have some objects to play with and we can do some mathematics with. So a set is a collection of objects, that's all it is. And the objects in a set we're going to call elements. And we write them in a couple of ways, which I'm going to talk about now. So to describe a set, there's two ways. The first way, actually there's three ways. I'll talk about two right now, and then I'll talk about the third. So the first way is just listing all elements. And so, let me give you an example of that. So let's say we just wanted a set with the numbers 1, 2, 3, and 4 in it. So we'd write it like this. So these are our open and closed set brackets, and these elements in here, they're what's in the set. You can think of it as a list of what's in, say, a bag. There's no real order inside of a set. This is unordered. So you're thinking of this something like this. So here's our bag, and this list here tells us what's in it. There's a 1, a 2, a 3, and a 4. So that's how you're thinking of a set. And I'll just say this is the same thing as if you had the order changed up, maybe 2, 4, 1, 3. That's the same set. And remember, this is a list. So if you say there's a 1 in the bag, a 2 in the bag, a 3 in the bag, a 4 in the bag, if you said there was a 1 in the bag again, well, there already is a 1. You've already listed it. So it's already in there. So it's like you can think of it as almost being redundant. It's fine to put it there, but it is redundant. So all of these three sets are the same. So that's the first way of describing what's in a set. The second way is describing the elements. And we usually do this using something called set builder notation. And I'll explain what that is. So let me scroll here, get a little more room. So set builder notation is basically of the form where you list kind of variables for your elements, and then you have this line here, and you read this line as such that and then you have some sort of, I'll write it like this, P of X. But this is some rule to tell you what's in the set. So let's do the same one up here. In fact, I'm going to name this set A. So back up top, I'm going to name this set A. And I like to use this colon equals when I'm naming something. So if I want to give something a name of a letter, I will just write a colon equals with the colon by the side of the name and the equals by the side of the object. And that comes from computer science. Okay. So if I wanted to write A in set builder notation, I might write it like this. There's many different ways, but I could explain what's in it. So it's going to be numbers X. So they're numbers. And in fact, I'll even clarify here, they're counting numbers. So they're counting numbers X, such that, remember that line means such that, well, the counting numbers are going to be between 1 and 4 inclusive. So it's all counting numbers that are greater than or equal to 1, and less than or equal to 4. And of course, those numbers are 1, 2, 3, and 4. And again, you could describe this in a little bit different of a way. In fact, you could describe it in many ways. So counting numbers x, such that maybe we could write it like this. 0 is less than x is less than 5. So it's all counting numbers that are strictly greater than 0 and strictly less than 5. And those numbers are, of course, 1, 2, 3, and 4. Those are the only counting numbers that are greater than 0 and less than 5. So you can write down what a set is in set builder notation in many ways. So a little notation so we can talk succinctly about elements of sets. And as an aside here, usually, not all the times, but usually we'll write elements of sets using lowercase letters and the sets themselves using uppercase letters. So you could see a lowercase a meaning an element of an uppercase a meaning the set, something like that. That's not a hard and fast rule, but that's the one that tends to come up, especially in these lower level math courses. That tends to be how we use it. And there's going to be some frequently used sets of numbers that come up all the time. So let me kind of explain these. So the first one is, it's called the set of natural numbers or counting numbers. And I'm going to describe this by listing all elements in some sense. And I'll explain what I mean in some sense for a second. So it's your counting numbers. So it starts with 1, goes to 2, goes to 3, 4, 5, 6, 7, 8, 9. All the way as far as you like, because there are infinitely many counting numbers. So I put this little dot, dot, dot here to mean that the pattern continues. So when you use these dot, dot, dots inside sets, it just means, well, hopefully you can figure out what I mean by these dot, dot, dots by what comes before it. So this is the set of natural numbers or counting numbers. Another set that comes up is, well, the whole numbers or the natural numbers with 0. And there's lots of different notations for this, but I like using just the natural numbers with a little 0 down there. And this is, of course, the set of counting numbers with 0 at the start instead of 1. And that goes all the way to infinity as well. After that, well, we have our positive and negative counting numbers along with 0, and that's called the integers. Now, you could think, well, n for natural, how about I for integers? And some people do use that. But what's more common is this kind of blackboard bold Z. So these blackboard bold letters, they're usually used for sets of numbers, number sets. So let's write it in list notation, and then let's write it in set builder notation. Okay. So let's start with 0, and then it goes 1, 2, 3, 4, 5, 6, 7, all the way to infinity to the right. And we also have our negative numbers. So -1, -2, -3, -4, -5, all the way to the left. So this is kind of a doubly infinite set. It has no least element. These ones here have least elements, and that's going to be important quite a bit later in the course. But the integers do not. They do not have a least element. They're doubly infinite. Now in set builder notation, we can write it the following way. It's all numbers x such that, well, either x is a counting number, or sorry, a whole number, or the negative of it is a whole number. So that makes sense. So for example, if we had 1 here, well, 1's a number, and does it satisfy our condition for being in the set? Well, 1 is in the set of whole numbers. Here it is here. What about something like -5? Well, -5 lives in here. -5 is a number. Is it an element of the whole numbers? It's not. But its negative is. Negative of -5 is +5. And +5 is indeed an element of the whole numbers. It's in this set here. These ... dots kind of hide it, but you can tell it's there. The next set we have are your set of all positive and negative fractions we call the rational numbers. We use the letter Q to describe that. Now, this is a hard set to write down, listing all the elements. You can, in a way, but it is kind of complicated, and it gets into the idea of different types of infinity, which I don't know if we'll get into in this course. But it's kind of easy to write down in set builder notation. Well, it's numbers that look of the type a over b, such that, well, what can a and b be? Well, we want them to be integers, where a is an integer and b is an integer, and, well, remember, we can't have 0 as a denominator for a fraction. So we want b not to be 0. And of course, well, you could think, well, 1 over 2 is in this set, and 2 over 4 is also in this set. They're both elements of this Blackboard bold Q, but they're really the same number. 1/2 and 2/4 is the same thing. So we need a way of determining when two numbers are equal, so we don't kind of count these guys as different elements. So we say, and if a times d, and I'll explain these in a second, equals b times c, then these two fractions, a over b and c over d, are the same number. That one's a little complicated, and you can see why we're learning mathematics very slowly and accurately, even to describe the set of all fractions, to say, well, what are they? Well, they're an integer over another integer, but that's not enough. You need to say that the bottom integer, the denominator, can't be 0. And you have to say when two fractions are equivalent. And two fractions are equivalent when one numerator times the other denominator equals the other numerator times the first denominator. So they're the set of rational numbers. That's all your positive and negative fractions. Let's keep going. I'll talk about two more sets, and they're going to kind of be a little bit difficult to describe. Well, I shouldn't say that. This one is kind of difficult to describe, In fact, to really define this set, you probably can't do it properly, like really, really properly, until about third year of a mathematics degree. But I'm going to talk about this third way of describing sets, which isn't the best. In fact, you should only use it if you can't do it in the other two ways, or in really, really simple situations where it's very obvious, where you're not losing a lot of precision by doing this, but just describe in words what's in the set. And this is basically all numbers that can be written using decimals. So that's everything. So in the set, you're going to have things like 0. You're going to have things like 1, of course. You're going to have -3. You're going to have -2/7. Sure. You're going to have, what else? You can have square root 2. That's a number. And you can write that using decimals. You can write something like pi using decimals as well. Pi is like 3.14159. It goes on forever. Square root 2 is like 1.414 whatever, and it goes on forever. So all possible numbers you can write out with decimals is the set of real numbers. And the final one we're going to talk about, and I'm just going to introduce you to it, is the set of complex numbers. And these are basically like real numbers, except there's an additional part we add, and that is the square root of -1. We say we're allowed to take the square root of -1. So it's all numbers of the form a plus I times b, such that, let me tell you what these things are, a and b are any old real number you like, and I is a number such that if you square it, you get -1. So there are familiar sets of numbers. I can think of these as a diagram as well. So this is called a Venn diagram in some sense. So I can just put all of the sets in sort of a diagram where one is included in the other. We'll get into this in more detail in future videos. But let's do the natural numbers first. So here's the set of all natural numbers. There it is there. And you'll have things like 1 will be in there, 7 will be in there, 11 will be in there, 1,003 will be in there, whatever. They're just some examples. Then, of course, we also have the set of whole numbers, that natural numbers with 0. So you can add on a 0 here, just include 0 in that kind of bag, or however you want to look at it. So all of this, I'll just kind of dot over this. All of this is the set of whole numbers. It's just the natural numbers along with 0. Well, all of your natural numbers are also integers. So they're going to be inside the set of integers. So not only do you have things like 1 and 11 and 0, you also have negative numbers in there. So you'll have things like -3 and -22 and -1, whatever. So all your negative numbers are in the set of integers, but they're not in the set of whole numbers here. And of course, inside the set of rational numbers are the integers. So we'll do this in green. So all of this is the set of rational numbers. Well, -3 is the same as -3 over 1. Any fraction over 1 is just the numerator itself. So all of these guys, put them over 1, and you have yourself a fraction. Great. But there are numbers that aren't integers, that are rational numbers. Things like 1/2, or 3/7, or negative 5/2, or negative 1 over a million, whatever. So there are your rational numbers. Then you have the set of real numbers. So I'll do that in yellow. So all of your numbers that aren't rational, we call them irrational, they're going to be between the set of rational numbers and the edge of the real set. So things that are real numbers but aren't rational numbers are things like square root 2. You can't write that as a rational number. You can't write pi. You can't write, say, negative 1 plus square root 3. Whatever. Things that you can't write as a fraction or as a rational number. They're your irrational numbers. They're here. We not often they're given their own set name like we did here. Sometimes you'll see that, but for our purposes we won't use that. And then finally, well, you could imagine anytime b here is 0, you just have a real number. So all real numbers are complex numbers. So I'll do this and I'm at a color, so I'll just do this in black again. So inside of that set, you have your complex numbers. And here you have things like 1 plus I, or maybe you'll have just I, or you'll have square root 2 minus 3I, or you'll have 3/2 plus 7I, whatever. Anything like that, they're your complex numbers that aren't real, have an imaginary part. We call the I bit the imaginary part of the complex numbers. And this is how your number systems work. Let's do an exercise now. Let's try and describe the following sets using the other style of notation. Some of these we're just listing the elements. Some we have in set builder notation. I'm going to pause the video now and see if you guys can come up with a good way of doing this. Remember, for the ones that you're going to write set builder notation, A and C, you might have different answers from what I have and different answers from what each other has as well, but that's okay. So pause the video now and give these a go. Okay, now that we're back, the first one, well, we already did this in the previous slide. We know this is going to be something along the lines of, well, it's going to be natural numbers x, and we can use this new notation, natural numbers, such that they're the ones that are between 1 and 4 inclusive. So 1, 2, 3, and 4. This one, it's all natural numbers such that the natural number is less than 20 and it's a prime number. So these two conditions need to hold. And what do I mean by prime? Well, prime numbers have exactly 2 factors. That's probably the easiest way of saying it. So that means that 1 isn't prime, since 1 has just one factor itself, 1. 2 is prime, since 2 has exactly 2 factors, 1 and 2. 5 is prime, 5 has exactly 2 factors, 1 and 5. 3 is prime. 9 is not prime, since it has 3 factors. It has 1 and itself 9, but it also has 3 as a factor, since 3 times 3 is 9. Okay, so now that we talked about prime numbers a little bit, well, we want to just list all natural numbers such that they're less than 20 and they're prime. So we can just go through. 2 is prime, 3 is prime, 4 isn't prime since 2 times 2 is 4, 5 is prime, 2 times 3 is 6, so it's not prime, 7 is prime, 2 times 4 is 8, 9 is prime, 2 times 5 is 10, 11 is prime, 4 times 3 is 12, 13 is prime, 14 isn't, 2 times 7 is 14, 3 times 5 is 15, 4 times 4 is 16, 17 is prime, 9 times 2 is 18, 19 is prime, and 20 is not. So that is the set written in list notation. For C, well, there's lots of different ways of writing it. But if we wanted to describe it in words, rather than just saying it's 2 and negative 2, we could say it's all integers, so that when you take the absolute value of them, you get 2. That's one way of doing it. And a good way of coming up with set builder notation is just speak aloud what property all your elements in your set have in common, and then just figure out how to write that mathematically. We said it's all integers, where if you take the absolute value of them, you get 2. So let's write that. So it's all your integers. So x is an element of your integers, such that, so the condition that they're in this set is that if you take the absolute value of them, you get 2. That's one way of writing it. There are other ways, but this is a good way of stating it. All right, for the final one, let's read what it says. It's natural numbers such that, well, the natural number equals 2 times a, and now it's going to tell us what a is. Well, a is some other natural number. So this means that it's all natural numbers that can be written as 2 times another number. And if you think about it, what does this mean? Numbers that can be written as 2 times some other number, well, what are they? Well, 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8. Well, they're all your even numbers. This here is the definition of your even numbers. It's numbers that can be written as 2 times some other integer. So we know what that's going to be. That's going to be 2, 4, 6, 8, 10, 12, 14, 16, all the way to infinity. So the next thing I want to talk about is the idea of the empty set. And that's just the set with nothing in it. It's just, if you're thinking of it in kind of that bag idea that we talked about in the previous slide, it's a bag with no elements in it. There's nothing in this bag. And you can write it in 2 ways, either as a circle with a line through it, like here, or as an open and closed brackets with nothing between them, as in here. Both ways are good to go. Now, the next example I want to do, and I guess I'll label this. This is example 1.2. Let me put that in there. Well, let's say we have this set here, and I described it in list notation. These are all of the elements of the set, and I want you guys to determine if the following 6 statements here are true. Now, before we do that, let me write this, because we're dealing with this just for the first time, in kind of that bag notation, that bag idea. So S is going to be a bag. And what's in this bag? Well, a 1 is in this bag. A B is in this bag. A 4 is in this bag. And then we have, well, another set in this bag. And this set has the elements 1, B, and 2 in there. And that's allowed, even though we have a 1 in our list already. If another 1 is inside of another set, that's still allowed. So we have a 1, we have a B, and we have a 2 here. And finally, we have one more set. We have the empty set. So we have a bag with nothing in it also inside. So that's everything that is in S. So maybe now pause the video and try this example. See if you can determine which of these statements are true. Okay, well, the first one, is 1 an element of our set? It indeed is. Here it is here it is in our bag. This one is true. Is 3 an element of our set S? No, definitely not. There's not a 3 to be found. This is not an element. Is the set 1b2 an element of our set? Well, let's see about this. If I put my hand in this bag, can I pick out in one go the bag containing 1b2? In fact, I can. Here it is. There are 5 things I can pull out. I can pull out a 1, a b, a 4, this bag or the set containing a 1b and a 2, and this bag containing nothing, or the empty set. So one of those things is this bag containing 1b and 2, so this is true. The empty set, I can pull that out. Here it is. Here's our empty set. I can pull that out. 2. Now I can't pull out a 2 because there are only 5 things in this set. The 1, the b, the 4, this bag containing stuff. Even though there's a 2 in here, I can't reach inside of that bag first. So I can't take out just the 2. And we have the empty set. So even though 2 is inside a set that's an element of this set, it's not an element itself. So 2, that's the wrong one, 2 is not an element. And for similar reasons, the set containing just 1 and b is not an element, because the set containing just 1 and b, the set containing 1 and b also has a 2 in it here. So there's no way for me just to take out the set containing 1 and b. The next concept I want to talk about is the cardinality of a set. And that's just a fancy mathematical word to talk about the number of elements in a set. And the way we write it is like the absolute value, except it's of a set and not of a number. So these kind of vertical bars surrounding a set, that means the cardinality, how many unique elements are in a set. So let's just do a couple of examples first. So easy one. So the cardinality of set A, B, C is indeed 3. There are 3 elements in the set A, B, C. And remember, it's unique. So if we have the set A, B, C, we care about only unique elements. So the cardinality of this set is also 3. We don't count A twice. We just say, well, there are 3 elements, A, B, and C. A just got listed again for whatever reason. So, and let's do one more, I guess. Well, what about, say, the integers? Well, we know there are infinitely many numbers. Infinitely many integers, in fact. So the cardinality, we say, is infinite. And from there, it leads us to our next example. Let's find the cardinality of the following 4 sets. Again, pause the video, give it a go, see if you can work out the cardinality of each of these. Okay, now that we're back, well, the first one, this is the same set from the previous slide, so we know the cardinality of that. We counted them, there were 5 elements. Those 5 elements were 1, B, 4, the set containing 1, B, and 2, and the empty set. So the cardinality is 5. It has 5 elements. Set A2 also comes from a previous slide. It was the numbers that are prime and less than or equal to 20. And they are, of course, and I should say the natural numbers that are prime and less than or equal to 20. And they are 2, 3, 5, 7, 11, 13, 17, and 19. And there are 8 numbers there, so the cardinality of the set A2, 2, 3, 5, 7, 11, 13, 17, 19, that's 8 numbers. Well, how many fractions are there? Of course, there are infinitely many fractions. So the cardinality of this set, the rational numbers, is of course infinite. And the cardinality of A4, well, what is this? It's numbers that are natural numbers that are even, prime, and greater than or equal to 5. Well, we know numbers that are even, 2, 4, 6, 8, 10, etc. Well, how many of those are prime? Well, just 2 is prime. Every other number can be written as 2 times something. That's the definition of being even. So right now, just satisfying these two conditions, being even and prime, limited us to one number, just 2. But we also need that the number is greater than or equal to 5. So there are no numbers that are even, prime, and greater than or equal to 5. So since there are no numbers, we know that the cardinality of A4 is 0. It has no elements. What does that mean? That means that A4 is indeed the empty set. There's nothing in it. So it's the empty set. All right. The next thing I want to talk about is the idea of a subset. And this will be the last concept I want to introduce in this video. So a subset you can think of as a potentially smaller set than the set that you're given. And by smaller, what I mean is that every element of A is also an element of B. If A is a subset of B, then that happens. Let me kind of give you an example to make sure we understand what's happening. So let's do this in blue over here. So if, say, B was the set A, B, C, and D, and let's say A was the set A, D, and let's say C was the set A, B, E. Well, let's look at A and B. Is A a subset of B? So we have to ask if every element of the first set of A is also an element of your second set. Well, little a is an element of B. Little d is an element of B. So all of the elements of A are also elements of D. So this is indeed a subset. Is C a subset of B? Well, in this case, it's not. Even though little a is in B, little b is in B, little e is not. So there's an element here that isn't in the set B, so C is not a subset of B. And to say something is not something in math, you usually just put a little line through it like that. It's a very useful symbol. And the final thing, well, is B a subset of itself? Let's see if it satisfies the definition. Is every element of B also an element of B? Well, A is an element of B, B is an element of B, C is an element of B, and D is an element of B. So the set is a subset of itself. In fact, every set is a subset of itself. This always holds. You can think of it almost like the set version of less than or equals to. In fact, this symbol here kind of reminds you of a less than or equals sign. Instead of a sharp corner, it's a rounded thing. But just like with a less than or equals, we put the smaller thing on the smaller end and the bigger thing on the bigger end. So that's how it works. And in fact, we could draw a little Venn diagram here, in fact. If this is B, and it has the elements A, B, C, and D in it, then A is this set here. It's contained wholly in B. So that's why A is a subset. Set C I'll do this in green. That's A, B, and E. So there's an element E somewhere out here. And set C looks like this. It's not wholly contained in B, so it's not a subset. So let's do the example here. I'll let you guys try it yourselves before you watch the rest of the video. We have the set here, A, and it has the elements 1, 2, 3, a set containing 1 and 2 and 4, and determine if the following are true. And I guess I should make a note here. I didn't go over this yet. But the empty set is always a subset of any set. And we'll talk about why that is in the next few videos. It has to do with some logic stuff that we'll get into. But the empty set is always a subset of any set. So know that. Okay. So knowing that, determine which of the following of these 6 are indeed true. So again, pause the video and try it now. Okay, now that we're back, let's go through it. Is the empty set an element of A? Well, the elements of A are 1, 2, 3, the set containing 1 and 2, and 4. There's no empty set, so this isn't true. What about B? Is the empty set a subset of A? Well, the empty set's a subset of every set. So that's always true, no matter what. That one was easy. Is the set containing 1, 2 an element of A? So remember, that means, can we find exactly this in the list of elements of A? And we can. We have the set containing 1, 2 here as an element. It's kind of the 4th in this list. In the way it's listed, remember, there's no real order to elements in a set, but it's 4th in the way we wrote it down. So this one is indeed true as well. Well, is 1, 2 a subset? Or the set containing 1, 2, is that a subset of A? Now remember, what does it mean to be a subset? It means that every element of the smaller set, or the potentially smaller set, is also an element of the potentially larger set. So we have to ask, is 1 an element of A, and is 2 an element of A? Well, 1 is an element of A. Here it is. Is 2 an element of A? Sure. Here it is. That's all the elements. We've checked them all. That's what you have to do when you have a subset thing. You're looking, check if all of them are elements. So this is indeed true as well. Okay. The 5th one is the set containing 1 and 2 an element of A. Well, not really. In fact, it's definitely not. Here we have the set containing 1 and 2, or you can think of it as a bag containing 1 and 2, but we don't have a bag containing a bag containing 1 and 2. They're different things. Let me kind of draw this out. So A looks like this. Here's our bag. Here's our 1, our 2, our 3, our bag containing 1 and 2, and our 4. And this here, this set containing the set containing 1 and 2, that looks like this. It's a bag containing a bag containing 1 and 2. And that's not an element of A. So this is false. All right. Well, is the set containing 1 and 2, is that a subset of A? Well, how many elements does this set have? It has exactly 1 element. It just has the set containing 1 and 2. That's the only element of this set. And I have to ask, is this, the set containing 1 and 2, is this an element of A? Let's check. Oh, look, here it is. So this is indeed a subset of A. So that one is true as well. And that's our little introduction to sets. We're going to go over this in a lot more detail in the coming lectures, so stay tuned. But just knowing these concepts allows us to do a little bit when we talk about logic, which will be in the next few videos.